project I'm going to share with you guys is one we did. We started this in 2010. We completed it in 2011, so almost 10 years down the road. It was for a local company packing blueberries, Eurofruit Local, and John Ackerman did that article in 2012, and at that stage, the company was called Refrigeration Solutions, that subsequently become part of Energy Partners, and Eurofruit Locals also diversified. So things have changed a bit, but basically their focus was packing blueberries. And at that stage, the blueberry market in South Africa was really in its infancy, and it's expanded dramatically subsequently. And really high value product. You could have 3 million rands worth of blueberries in a relatively small cold room. And so the client was really into, firstly, saving operational costs, and of course other reasons. The rate of dehydration was really an issue to him. His current direct expansion systems were operating with R22 was very much a problem. So we had to come up with a solution, but fortunately he was very open to any suggestions. Okay, so more recently, you had a publication on low charge ammonia systems. We certainly attempted to have the charge in that case as low as possible for many reasons, but primarily, of course, the toxicity of ammonia is a concern. So we needed to keep the charge very low, although low charge ammonia systems, that wasn't really a buzzword at the time. More recently, from your document, what defines it? So you can look at it in terms of grams per kilowatt hours, per kilowatt of cooling, but of course you operate at different suction temperatures. So if you refer to kilowatts, what are you referring to? -10, -30? So it's difficult to define. The alternative is to refer to the charge. Similar to the hydrocarbon solutions. And basically, I think what comes from your document more recently is you consider it low charge if it's smaller than 150 grams per kilowatt. At the time, a huge source of information for me was from that book, that publication from Dr. Volkmar Haase. So we put that on the SAIRAC website as well. Only thing that's beginning to date a bit in that book is the information regarding transcritical CO2, but a hugely valuable source of information. It covers hydrocarbons, it covers so much information, so that was really a huge source of information for myself. And then why ammonia? So you've heard ammonia, only refrigerant here, 0 global warming potential, 0 ozone depleting potential. The only one that we're aware of. So I think one thing that makes ammonia very energy efficient is the latent heat of vaporization. So if you take a kilogram of high pressure liquid that changes phase and absorbs heat to vapor, and you compare it with R22 as a reference, now 404 does a little bit better, 16% better in theory, 410. Then you get quite a jump. R290 is significantly better. Hey, CO2, no, I think we're in the right place today, but of course ammonia is way better than the rest of it. No? So if you look at it from that perspective, it's very appealing. And of course, now this illustration from article from Andy Pearson is very good, because ammonia has always been there. It's always been there since the late 1800s. You see there was CO2. It's a bit higher up, but CO2 was commonly used, and you see 2 gaps there, and that was pretty much 2 quite devastating wars that the world struggled with. And then in the 90s, CO2 became more popular again, but ammonia was there all the time. This is the site where the client, so basically we customized the solution for the client. This was his site in the process of being built, and basically that's a similar view. So we placed the plant on top there. Sorry, the picture maybe isn't very clear, but The plant room is on top there. You can see the evaporative condenser generator at the bottom. So if you had a leak, and the likelihood of the southeaster blowing there is very good. If you had a leak in that plant room, it would all just blow away at such a rapid rate. So that's the safest location we could possibly locate the plant room at. So it's an ammonia system, but of course in this case the ammonia is contained in the plant room. So it's a secondary cooling system. We're not circulating ammonia into the pack house, which made it significantly safer. One peculiar thing the client wanted, he wanted to simulate the glass door fridges that his clients have, that Woolworths has, and then he would label the produce that he sends off and date it, and you know, if he's got a complaint from Woolworths, then he can go check his sample in his fridge. Mistake we made there, you see there's a window at the back, and the architect or the interior decorator wanted to see the nice wall at the back, so we cut a hole there, and actually that messed up the heat load calculations quite badly, and no, so it looked pretty, but yeah, that was definitely a mistake I won't make again, and all the cockroaches fell in the back, so that was really difficult to get them out. And sorry, you see at the top there's a motorized valve. So you see that orange motorized valve, that's a two-way valve, so you've got supply and return. And on the outlet, we had a diaphragm valve, just to try and balance the system out. Because we're circulating water and glycol from the plant room, and of course, it's quite a skill to design the secondary cooling system to have an even pressure drop throughout. So we have motorized valve, so basically, when you reach set point, motorized valve closes, and so you get your set point and your differential. So motorized valve opening and closing, hovering around your set point all the time. So every air cooler had a motorized valve, and of course a supply and a return line above the ceiling level. Okay, I don't know if you can see that too clearly, but evaporative condenser, as is normally the case with an ammonia system. And we designed for an operating condition of -10. So we actually edged that up a bit. We didn't really need -10 to maintain a room temperature of 0. So condensing, our target was 32 degrees. Mistake we made in Stellenbosch, you know, a wet bulb of 22 was a little bit too marginal. On a really hot day, fortunately we had variable speed drives on the evaporative condenser, so we could get more air through there and lower the condensing. So that saved my bacon on that side. And of course, the secondary coolant was water and propylene glycol. Ethylene glycol, I believe, is really toxic. So, yeah, so supply at -6, return at -2, 2 compressors at 70 kilowatt. That's basically what it looked like in our workshop. And you can see we welded it all on a skid, and you can see the Bitzer compressors, the 6-cylinder machines at the corner at the bottom on the left-hand side there. Key in this case was the evaporation with our heat exchanger. On the low pressure side was a unit from Vatherus, and this was a suction accumulator heat exchanger combination. Basically, in this case, you can see there on the illustration, the circular heat exchanger was flooded, and the alternative was a heat exchanger with an accumulator above it. So you can see the blue unit is a lot more compact. That's the shop drawing. Okay, so basically the key in this case was we had a level sensor, and we're maintaining the ammonia level in that heat exchanger. And our level sensor, of course, sends signal to the controller, opens the expansion device, and that feeds liquid into the heat exchanger. So we're basically maintaining, see that black line, we're maintaining that level constantly. You see on our, you can see on our, sorry. So,
you got to stop now.
Yeah. Okay, so our ICM valve is our expansion device in this case. So of course you see that yellow pipe, that's our high pressure liquid feeding to the expansion device, and that expansion device then feeds the heat exchanger. So we basically electronically control the liquid level. And in this case, we have a range of 280 mil. We had no liquid receiver. That drain line you see there, that is the drain line coming from the evaporative condenser. So we have no liquid receiver in this case. Oil drain with a dead man's valve. In this case, we didn't do automatic oil return. There's the ICM valve. So basically, that's your expansion device. High pressure liquid on the one side, and of course, then feeding liquid into your expansion device. That's just a little bit clearer, but basically, you want to maintain that level in the heat exchanger. Handy feature is a flow meter. Very handy if you have a secondary cooling system. You walk in the plant room door, you see that orange float. If it's all the way up, you have maximum flow. If it's down, if there's air in the system, you can see it. Very, very handy to see. I'll just light, that's the inlet to the plant room. Thing we added at a later stage was a tank, a makeup tank at the highest point of the system, just to get air out of the system. It's really difficult with a secondary cooling system. And yeah, so I think what you want to see briefly, just as energy review, basically we estimated 1,200 rands per day for the ammonia system, and then the other extreme was a 1348 direct expansion system. So what we estimated and what they actually ended up using was fairly accurate, but they had operational factors like working on a Saturday that was difficult to factor in. So 320 grams per kilowatt hour. Refrigerate was limited to the plant room, and of course the dehydration was really a big issue to this client. And in no electrical defrost. That's really a significant saving in energy because your air coolers doesn't ice up. So very moderate icing there, and more accurate control of the room temperature, especially if you have a high value product like that. Okay, that's it.
So no issues, right? This has been running quite a few years now.
Almost 10 years, yeah.
So, I mean, part of this was to be able to demonstrate that the results were working.
Yeah.
It's not just for 1 year, but for multiple years.
Yeah.
So it's delivered.
Yeah, it's actually a project we did for GIZ a year prior, and the learning from the GIZ project is what we actually applied in that case.
Okay, and have you applied this elsewhere?
Yes, one other site. So this site was 140 kilowatt, another site was 110. So in ammonia terms, that's quite small. Yeah. I don't think you have too many 110 kilowatt ammonia plants.
All right, okay. Thank you, Marius.